Welcome to the next video on signals and systems. KTU solved questions from pros and experts. Okay, the question is, determine the exponential Fourier series representation of the half-wave rectified sine wave as shown in the figure below. So below you can see a sine wave which is half-wave rectified with a time period of t. The time period is definitely t, capital T. So I can write all that I know from the question. So the time period is t, time period is equal to capital T. Therefore, angular frequency, fundamental frequency is 2 pi by t. That we know. Okay. Then what else? Then you can see the question asked is to determine the exponential Fourier series. So what is the expression for exponential Fourier series? X of k is 1 by time period integral over 1 complete time period, which is 0 to t. But you can see up to 0 to t, the full length signal is not there. The signal is present only up to t by 2. Okay, so I can write instead of 0 to t, the signal exits only up to t by 2. So 0 to t by 2. And what is the signal in that interval? It is sine t, right? Sine omega 0 t. But what is omega 0? It is 2 pi by t. But wait, I can write, okay, or I can substitute the value 2 pi by t later. For the time being, for the convenience of calculation, I can write sine omega 0 t dt. Okay, wait. Sine, okay, this is x of t into e raised to minus jk omega 0 t dt. Okay, so this is the expression for the Fourier series coefficients, and we can also always find a0, which is the DC component, as 1 by time period integral over 1 time period, but here it is only up to 0 to t by 2 x of t dt. Okay, x of t dt, but instead of x of t, I'm writing it as sine omega 0 t dt. Sine omega 0 t dt. Okay, so first we can start finding x of k. So x of k is equal to, we can use this expression to find out the Fourier series coefficients for x of t. So x of k equal to 1 by t, time period is t, integral over 0 to t by 2. I can write this integral as e raised to minus jk omega 0 t into sine omega 0 t dt. Okay, now this is a very a big integral with so many steps. So I can tell you a result. If you can just remember this, it will be useful in many subjects, not only in signals. So if integral e raised to at into sine bt dt is asked, you can remember this result. The value will be always e raised to at whole divided by a square plus b square into a sine bt minus b cos bt. This will always be the result of this integral. Okay, so what we have in our problem is e raised to at into sine bt dt form. So I can write the result similar to this thing, this expression, and put the limits from 0 to t by 2. That's what I'm going to do. Okay, so I can write here in our integral a is equal to minus jk omega 0 and b is equal to omega 0. Okay, so with the help of this expression, I can rewrite this expression as 1 by t into integral 0 to t by 2 e raised to minus jk omega 0 t into sine omega 0 t dt becomes e raised to a into t. A is minus jk omega 0. So e raised to minus jk omega 0 t divided by a square plus b square. A square is actually minus jk omega 0 whole square plus b square. B square is b is omega 0, so b square is omega 0 square. Okay, into a sine bt. A is minus jk omega 0 into sine bt. B is omega 0, so omega 0 t minus b cos pt. B is omega 0, so it is a symbol to write omega 0 cos omega 0 t. Okay, now we can simplify it. 1 by t, actually this is under the limits 0 to t by 2. I think after some more simplification we can put down the limits. So e raised to minus jk omega 0 t whole divided by what is minus jk omega 0 square. It is minus jk omega 0 square is plus jk omega 0 square, because minus square is plus, so j square, I can write it here, j square k square omega 0 square will be the resulting. Minus will be gone because it is squaring. Okay, so j square is actually minus 1, so minus k square omega 0 square plus omega 0 square, okay, into minus jk omega 0 sine omega 0 t minus omega 0 cos omega 0 t. Okay, now I think we can put the limits from 0 to t by 2. Okay, 0 to t by 2. So this becomes, that is equal to 1 by t, applying the first limits, upper limit e raised to minus jk omega 0 into t by 2, okay, divided by omega 0 square into, I can simplify it as omega 0 square into 1 minus k square. Okay, that will be there, into, now it is minus jk omega 0 into sine omega 0 t by 2, because I am putting the limits for t, upper limit as t by 2, minus omega 0 cos omega 0 into t by 2. Okay, this is by putting the upper limit, minus, now I can put the lower limit. Lower limit is 0, so e raised to minus jk omega 0 t into 0 becomes 1. Okay, so 1 by, again, omega 0 square into 1 minus k square, okay, into, now put t equal to 0, so sine 0 is 0, this term becomes 0, plus omega 0 into cos omega 0 into 0. Cos 0 is 1, so it becomes plus omega 0. So plus omega 0 means here it will be plus. Okay, so we have put down the limits. Now we have to be very careful. That is a very useful relation, because omega 0 equal to the, what is the expression for omega 0? Omega 0 is always omega 0 equal to 2 pi by t. Okay, so cross multiplying, what you will get is omega 0 into t. I can write it here, omega 0 t will be always equal to 2 pi. Okay, so wherever in the expression you find omega 0 t, you can confidently substitute 2 pi for it. Okay, so I can write it as 1 by t e raised to, here you can find an omega 0 t. Okay, so you can put 2 pi there, so 2 pi 2 cancel, so e raised to minus j k pi, okay, divided by omega 0 square into 1 minus k square, okay, into, again inside the bracket, minus jk omega 0 into, there is a sine omega 0 t here, so it is sine 2 pi, sine 2 pi by 2, that is sine pi. Sine pi is always 0, so I can write as 0, minus again omega 0 into cos omega 0 t is 2 pi, so 2 pi by 2 is cos pi. What is cos pi? Cos pi is minus 1, so we can write plus omega 0 here. Okay, plus 1 by omega 0 square into 1 minus k square into omega 0. Okay, now it's a matter of only a few more steps of simplification. So this is 1 by t into what is e raised to minus jk pi. E raised to minus jk pi is minus 1 to the power k. Okay, it's always minus 1 to the power k by omega 0 square into 1 minus k square into omega 0. This term is 0, so what here is left is omega 0. So omega 0, and I can cancel omega 0 and omega 0 here, plus omega 0 by omega 0 square into 1 minus k square. Okay, and again I can cancel an omega 0 on the numerator and denominator. So what we are facing is an expression having minus 1 to the power k plus 1. I can join this because the denominators are same, into omega 0 into 1 minus k square. Okay, now from the question we have already found that omega 0 was equal to, we know omega 0 is equal to 2 pi by t because the time period is t. Okay, so substituting 2 pi by t for omega 0, we can reach the final expression x of k is equal to 1 by t. I can write it as, okay, I can write it as minus 1 to the power k plus 1 divided by 2 pi by t into 1 minus k square. Okay, 2 pi by t into 1 minus k square. So this t gets cancelled. Okay, that implies finally x of k is equal to 1 by 2 pi into minus 1 to the power k plus 1 by 1 minus k square. Okay, so the Fourier coefficients have been found out. Now one more term is to be found out. It is the DC component or 0th harmonic, or we can denote it as A0 or X of 0. It is the 0th harmonic or DC component. We call it DC component. It is obtained by the equation 1 by t over integral over one time period 0 to t actually, but in this question it is only up to t by 2. The signal after t by 2 to t is 0, so 0 to t by 2 integral, then x of t dt. X of t is sine omega 0 t dt. Okay, now obtaining this integral, it is integral sine omega 0 t dt is minus cos omega 0 t by omega 0 within the limits 0 to t by 2. Okay, so this is minus 1 by t into what is omega 0 actually? Omega 0 is 2 pi by t. Okay, cancel t. So applying the limits, it is cos omega 0 t by 2 minus cos 0, which is 1. Okay, so this is minus 1 by 2 pi into, again we can see on omega 0 to t here, which is 2 pi, and 2 pi by 2 is cos pi. Cos pi is minus 1, so minus 1 is minus 2. Okay, so this is 1 by pi. So the DC value or DC component of this signal is 1 by pi, which you can see is perfectly in accordance with what we have observed in, or what we have studied detailed in a half wave rectified sine wave. The average value V average will be equal to Vm by pi for half wave rectified circuits. Here Vm equal to 1, so that will give you 1 by pi as the average value. Okay, so that's the answer. Okay, let's check the next question. State and prove the Parseval's theorem for continuous stamp Fourier transforms. Okay, we have already seen the statement and proof for Parseval's theorem, which was in Fourier series. The question was for Fourier series, but here the question is specifically asked for Parseval's theorem for Fourier transform, CTFT. Okay, so let us start doing this. First, the statement is, Parseval's theorem statement is, the energy of a signal is preserved in all domain, is preserved in either domain, whether it is time domain or frequency domain, the energy is preserved. That means energy of a signal, you know what is the energy of a signal? How can you find out the energy of a signal in time domain? It is integral over minus infinity to plus infinity mod x of t square dt. Okay, so that will be equal to integral minus infinity to plus infinity mod x of omega the whole square d omega scaled by 2 pi. I mean scaled by 1 by 2 pi, where x of omega is the Fourier transform of x of t. Okay, so similar to what you find in the time domain, the energy will be same but scaled by 1 by 2 pi. Energy will be same if you calculate the energy from the frequency domain also. Okay, in time domain you integrated the signal from minus infinity to infinity, what the square of the modulus of the square of the signal. In a similar way, if you find the Fourier transform and if it is integrated from minus infinity to infinity, x of omega square d omega, then again you will get the same energy. So that's why I'm saying energy is preserved both in time domain as well as in frequency domain. Now let us start to prove this. Let me start with the LHS. Integral minus infinity to plus infinity mod x of t the square dt. I can write it as integral minus infinity to infinity x of t into x star of t. Okay, where x star of t is the conjugate of the signal x of t. Always x of t into x star of t will give you the modulus of x of t the square. Okay, now let us see what is x of t and x star of t. Using Fourier transform equation, x of t equal to 1 by 2 pi integral minus infinity to plus infinity x of omega e raised to plus j omega t d omega. Okay, this is how you represent any periodic signal, non-periodic continuous time signal in Fourier transform. Okay, so if you know x of t is this thing, and x, then what is x star of t? What is the complex conjugate of the signal? It is 1 by 2 pi integral minus infinity to infinity x of omega becomes x star of omega, because that is the complex part. Okay, and e raised to plus j omega t becomes e raised to minus j omega t d omega. Okay, that's what you will get if you take the conjugate of x of t. Okay, conjugate of this signal becomes 1 by 2 pi, x of omega becomes x star of omega, and e raised to plus j omega t becomes e raised to minus j omega t. Okay, I think that's clear. Now what is for your additional information, I can always remind you x of omega is equal to integral minus infinity to plus infinity x of t e raised to minus j omega t dt. Okay, this will be needed in the upcoming steps of the proof. So having these three results in hand, I have started with the x of t square mod x of t square, and I have written it as x of t into x star of t. Okay, now that is equal to integral minus infinity to plus infinity x of t into I have already written an expression for x star of t as x star of t equal to 1 by 2 pi this integral. So I can replace it as that integral 1 by 2 pi 1 by 2 pi. Instead of x star of t, I am writing 1 by 2 pi integral minus infinity to plus infinity x star of omega into e raised to minus j omega t d omega. Okay. Now this is equal to integral minus infinity to plus infinity. I'm going to just organize or reorganize some terms inside this integral. So I'm first writing x star of omega. Okay, x star of omega, or I'm taking 1 by 2 pi outside also. It's a constant. So 1 by 2 pi integral x star of omega into d omega into next integral minus infinity infinity. What are the terms left? It is x of t into e raised to minus j omega t dt. Okay, so this is 1 by 2 pi integral minus infinity to plus infinity x star of omega d omega into, what is the next integral? Integral minus infinity to plus infinity x of t e raised to minus j omega t. I've already written it as x of omega. Okay, so I can replace it as x of omega. Right, so now this is very simple. 1 by 2 pi integral minus infinity to plus infinity x star of omega into x of omega d omega, which is nothing but 1 by 2 pi into integral minus infinity to plus infinity. What is x star of omega into x of omega? It is always mod x of omega the whole square d omega. So that is the RHS, and we have proved the theorem. Okay, we can consider the next question. Let f50 be a signal with a spectrum as shown below. There are 3 sub questions. What is the Nyquist frequency? That's the first question. What is the Nyquist frequency in hertz of the signal f50? Okay, so I can redraw the spectrum of the given signal f50, that is f of omega. Okay, from the question, this is the Fourier spectrum of the given signal f50, denoted by f of omega, and it is plotted against omega, which is the angular frequency given in radian per seconds. Okay, now let us look at the question. In all the questions, the Nyquist frequency is asked in hertz. Again, in question B also, fs is 200 hertz, 400 hertz. Okay, so all the questions are asked in hertz and not in radian per second. So I think it will be safer if you convert the entire spectrum into hertz, right? Hertz instead of omega. Okay, and how can you convert omega into frequency hertz? We have the equation omega equal to 2 pi into f, where f is the linear frequency. Okay, that implies f is equal to omega by 2 pi. So wherever you find omega, you do divide by 2 pi, right? You just do divide by 2 pi, and then you will get frequency, linear frequency. Okay, so 300 pi by 2 pi is 150 pi. Okay, this is 150 pi. Here it is minus 150 pi. Okay, so that's how you convert omega into frequency. So I can change it in frequency domain, frequency units. Okay, so this is the Fourier spectrum in frequency domain in hertz. So 300 pi by 2 pi is 150, and minus 300 by 2 pi is minus 150. Okay, fine. So from the spectrum, it can be easily deduced that the maximum frequency component of the message signal denoted by FM is 150 hertz. Okay, 150 hertz is the maximum frequency component of the message signal, or f of t. Okay, now if you know Nyquist criterion, what is Nyquist criterion? Nyquist criterion is the critical criterion for a sampled signal. From the signal you can reconstruct the original signal. Okay, it is the critical condition for sampling to be perfect, or a reconstruction is possible from the sampling. So Nyquist frequency or Nyquist criterion says that the sampling frequency should be equal to 2fm, or else the signal will be aliased, or it cannot be recovered from the samples. So fs should be equal to 2fm. that implies fs is equal to 2 into maximum frequency is 150 hertz dot. Okay, so 2 into 150 equal to 300 hertz. So the Nyquist frequency or Nyquist criterion is 300 hertz, and that is the answer to question A. Okay. And now what does the sub question B say? It says suppose the signal is sampled by an impulse train. You're given an impulse train. You don't get worried on seeing this. This is just an impulse train equation that is used to sample a signal. It's an ideal sampling. Okay, where t is the sampling period and fs is the sampling frequency. You're given fs is the sampling frequency. Then the question is to sketch, to plot the spectrum of the sampled signal with the first fs is equal to 200 hertz, and again fs changed to 400 hertz. So in these two conditions, you have to sketch the sampled signals spectrum. This spectrum is nothing but the message signal spectrum, and you have to plot the sampled signal spectrum for either of these two conditions, both of these two conditions, for fs equal to 200 hertz and fs equal to 400 hertz later. So before that, you might be having an intuition about what becomes to this spectrum when it is sampled. It is nothing but it will be repeated to infinite times on both positive and negative sides. Okay, and the repetition frequency is designated by or ruled by the sampling frequency. Okay, so I can help you to plot this. Okay, before finding out the spectrum for 200 hertz, I can give a rough idea about how the spectrum looks. So this was our original signal spectrum. We have already seen it as 150 hertz and minus 150 hertz. This is 0. Now if it is sampled, what happens to fs of t or fs of omega? Fs of omega, we are finding it in frequency domain. So this is f in hertz. Okay, so what happens to this spectrum? This spectrum gets repeated infinitely to both sides, positive as well as negative sides. Okay, this is what you are going to encounter when this signal with this spectrum was sampled. A replica, an infinite replica of the same sample is obtained to both sides. Okay, now how often it repeats? How often it repeats is denoted by the sampling frequency. This is sampling frequency. Okay, you find this is the exact center of the message Fourier spectrum, and after fs, exactly after fs hertz, you are getting the next triangle or next spectrum, its middle. Okay, this center to this center distance will be fs, right? Now the second triangle, you have its middle will be 2fs, 3fs, and so and it continues like likewise minus fs, minus 2fs, and so on. Okay, so this is an intuition about how the spectrum looks like when it is sampled. Now let us work out the question A. Fs equal to 200 hertz, how the spectrum comes. So I am drawing the message signal spectrum first. So this is message signal spectrum as it is. Okay, and we have already know it is 150 hertz. This is minus 150 hertz. Okay, now after sampling, this is repeated to both sides, infinite numbers. Okay, so what will be the spectrum at the next sampling frequency? I can denote it as the next sampling frequency. There will be another replica of the message spectrum. Okay, like this. Now my question is, what will be the frequency values at these points? What will be the values? From the middle of the first spectrum to second replica, the the value will be fs. This value will be fs, that is sampling frequency. But in the first question you are asked to find or plot it in fs as 200 hertz. So this is 200 hertz. Okay, this is 200 hertz. Now what will be this value? That value will be nothing but, you can see, 0 to maximum 150. So this length is 150. So naturally this length also should be 150. Okay, so what is 200 plus 150? It is 350. Okay, so I can write it as 350. Okay, and what is this value? This will be 200 minus 150, because this length is again minus 150. So 200 minus 150, that gives you 50. So I can write 50 here. Okay, but there is some problem. This is 150 and 50 is here, so I had to shift this to some left side. Okay, some more to the leftwards. So I can redraw it. See, so this end starts from 50 and it's like this. Okay, so this is 50 plus 150 is 200 is our fs, right? Then 200 plus 150, here it is 350. Okay, now what happens to the next spectrum, next replica? Next replica will be like this, very similar to this. It will start from somewhere here. Okay, you can find the values of the frequency. This value will be, I've already told you, it is 2fs. 2fs will be equal to 400 hertz, because 1fs was 200 hertz, so 2fs is 400 hertz. So here it is 400 plus 150 becomes 550, and here it is 400 minus 150, it is 250. Okay, right. And the same thing happens in the negative side also, like this. Again the values will be similar. This is minus 50, this is minus 200, this is minus 350, and here it will be minus 250, this is minus 400, this is minus 550, and so on. This continues. Okay, so this is the sampled signal spectrum when this signal is sampled at 200 hertz. You can clearly see a very important point, that is aliasing here. Aliasing, because our message signal spectrum was like this, and you can always reconstruct it ideally using a low pass filter, multiplying with the low pass filter in the frequency domain. So what results will be this thing, which is our message signal. But imagine of this spectrum, where if you are multiplying with a rectangular pulse or low pass filter, you will not recover this as such, because what you are going to express is, what you are going to encounter is multiplication with this signal in the frequency domain, and what results is not that triangle but something extra, some spurious components of other components will be there. So instead of this triangle, you will be getting this thing, which is not our message signal, so the reconstruction is not faithful. Okay, so this is called aliasing. So that's apart from our question number C. Specify whether the original signal can be recovered from samples in each case A and B. So case A we have already seen, it comes under aliasing criterion or aliasing property. So we cannot I can write the answer to question number C here itself. We cannot reconstruct or recover the original signal from the sample signal, in case A. In case A, where fs is equal to 200 hertz. Okay, why this is so? Because we have already proved that fs should be equal to at least equal to 2 times fm, right? 2 times fm, that is 300 hertz. We have already obtained in question A, solving question A, right? But here fs, instead of 300 hertz, fs is only 200 hertz, less than 300 hertz. So this is not obeying Nyquist criterion. That's why this signal had to encounter aliasing. Okay, so the original signal cannot be recovered in this case. Now let us see the case B, where the sampling frequency is raised to 400 hertz. Remember, 400 hertz is greater than 300 hertz. Okay, 400 hertz is greater than 300 hertz. So in this case, Nyquist criterion is obeyed. So let us see what happens. Okay, again I have drawn the message signal spectrum, which is just a triangle, and the values are 150 hertz, 150 hertz here, frequency is in hertz, and the minus 150 here. Okay, now when you are sampling the signal at fs equal to 400 hertz, okay, you can see fs equal to 400 hertz, what happens to the spectrum? That's our question. So what happens to the next replica? I can draw the next replica somewhere here. Okay, somewhere here. And what will be the frequency at this position? You know, it is always 1 fs, right? This is 1 fs, and fs is, at this case, you are drawing at fs equal to 400 hertz. So here it is 400 hertz. Okay, now what will be this value? That value will be nothing but, you know, this distance is 150. Okay, so 400 plus 150 is 550. Okay, and what will be this value? That value will be nothing but 400 minus 150, which is 250. Okay, and here you can see 250 is definitely greater than 150. There is no overlapping happening. Okay, so now what will be the next replica? I can draw it in another color. Okay, next replica is something like this. Okay, and we are interested in the frequency values of these boundaries. So what will be this value? What will be here? It will be 2fs, right? 2fs. This is equal to fs, and 2fs will be 800 hertz. So this is 800, which will be our 2fs. So what is this value? This is 800 plus 150, which is 950. And what will be this value? Here will be 800 minus 150, which is 650. Okay, so again there is no overlapping, and this continues. So the same thing I can draw in the negative side also. Here also. Okay, and again it repeats into infinity. Okay, the frequency values are again the same but negative sign. So this is minus 400, this is minus 250, this is minus 550. Similarly, this is minus 650, this is our minus 2fs, which is minus 800, and this is minus 950, and it goes on. Okay, so this is the spectrum of the sampled signal when it is sampled at 400 hertz, which is quite greater than the Nyquist criterion, which was only 300 hertz. And now you can see very clearly, if you're going to filter it or reconstruct the original signal, you can see original signal is nothing but having this frequency response, nothing other. These are not for the original signal. The original message signal contains only this frequency spectrum. So we have to recover only this frequency component. That will be our message signal. So if you're doing so, if you're multiplying this with a low pass filter, ideal low pass filter, okay, you can definitely, this is 1, the magnitude of this filter will be 1. So 1 into this triangle will give you the triangle itself. So the output will be the message signal itself. There is no any spurious components coming. So So we can answer question number C pertaining to this case also, case B also. What can be our result? We can definitely say that in this case, in case B, the original signal can be recovered from the samples. Can be recovered. Okay, because there is no aliasing here. And why there is no aliasing? Is because the sampling frequency is greater than 2 times FM. Greater than 2 times 150, that is 300. Okay, so that is the answer to this question.